Just looking at integration now. So integration and primitive functions. The last lesson we were looking at finding the primitive function. Now there is a link between the primitive function and finding areas under a curve. And that's explained by the fundamental theorem of calculus. So the fundamental theorem of calculus says if you want the area enclosed by this curve, the x-axis here, and the lines x equals a and x equals b. So if we want this area here, then what we do is we integrate or we find the primitive function of this curve, okay? So it's the integral of the function of x between the values of b and a. You always do the higher x value first and then the lower x value. And that equals, then once we integrate, we will do a substitution for the values of b and a. Little technical problem there. So we say the integral between x is b and a of the function of x dx is function of b minus function of a, where capital F function of x is the primitive function of x. So this allows us to find the area under a curve. Now, to be able to do that, you need to be able to integrate the curve. And we're going to see later today, there are some curves that we don't know how to integrate, but we'll be using other methods for finding the area under the curve. We're just going to quickly look at the proof of this. So if we've got a continuous curve here, if we're looking at the area under the curve, so let's say we've got a continuous curve here, y equals function of x, for all values of x greater than a, okay? So these are values of x greater than a. If we've got area A, B, C, D, see how that's the area under this curve here? It's shaded. So let area A, B, C, D be A bracket x. And then let area A, B, G, E, so this area here, A, B, all the way up to here, G, E, so that whole area, be A, area of x plus h, because this is x plus h. So this extra bit here is h. All right? Not saying we know the area yet, we're just doing that. Therefore, the area of this section here of D, C, G, E will be the large area minus the shaded area. Do we get that? Yes? No? All right. So what we can say is, we okay with that? So what we can say is that the area of DC, all right, now watching. We're trying to work out the area of DCGE, right? Now, what they've done here is they've drawn a rectangle below that area. If we look at the lower point here, actually, I'll draw that on my sheet to show you the other page in a minute. But if I'm trying to work out the area under here, right, we can say that that area is greater than this rectangle down here. Do you get that? So I'm going to go A, B, C, D, E. I'm going to draw another point in a minute. So I've got the area. Now I'm going to go back to that other page in a minute. But the area of rectangle DAEC wouldn't you, sorry, wrong one. The area of DABC, wouldn't you say, so that area, the whole bit under the curve, is greater than the area of DAEC? Did you get that? So the area DABC is greater than the area of the rectangle below it, but smaller than the area of the rectangle above it. So how do I know where to draw the rectangle below it? I just look at this point on the curve and come across here. Then I look at this point on the curve and come across here. Then I've got the big rectangle. So the shaded area under the curve is bigger than the lower rectangle, but it's smaller than the upper rectangle that I can draw, bounded by those points on the curve A and B. So area DABC is greater than area DAEC, but it's less than area, I'll call this point F. You tell me what's my higher rectangle. DFBC. Do Do you get that? Do we get that? Yes. So the area under the curve is bigger than the smaller rectangle, but smaller than the upper rectangle. So they're basically saying the same thing here. And I know they've got different, I've labeled it differently, but they've got the area of DCFE is less than the area of DCGE, which is less than the area of the upper rectangle, DHGE. Do we get that? Now remember, we can come up with expressions for this. So the area of DCFE is the lower rectangle. Can you tell me this width here? What's that width? H. And you know, if this is the point X, you know every point on the curve, just looking at point B, if I tell you the coordinates of point B would be A, comma, function of A. If this is y equals the function of x, then the coordinates of B are A, comma, function of A. The coordinates of x are x, comma, function of x, like, you know, the x value and the y value. And what would be the coordinates of G? X plus h, comma, function of x plus h. Do we want to draw that in now? Oh, anyway, just watch. Do you get that? So B would be A, comma, function of A. Point C would be, what's its x and y value? Point C is x, comma, function of x in brackets. And point G would be the x value and the y value, which is x plus h, comma, function of x plus h. Do we get that? Now, using that, we can work out the area of those rectangles. So, what is the area of the lower rectangle? What's this height? What would this height be? Isn't it function of x? Look, let's say this is the 0.53. Let's say C is the 0.53. Isn't the height 3? One sec. Down here is just zoomed in on not that first bit, but that second bit where you've got the x and the x plus h. You know how we've got that the area of DCFE is less than the area of DCGE, which is less than the area of the upper rectangle, which is DHGE. Okay, now we're going to come up with expressions for each of those areas. Okay, now the area, the coordinates of this point C are x, comma, function of x. We okay? The coordinates of G are, its x value is x plus h and its y value is function of x plus h. Now that means that this is x across, function of x up. So the length of this is function of x. And this width, as you've already told me, is h. So what is the area of the lower rectangle? Isn't it just function of x times h? So the area of the lower rectangle is function of x times h. That is less than the area, we don't know what this area is, of DCGE, which is less than, now I'm trying to zoom this. What's the area of the upper rectangle? What's this length? What's this length from there to there? How long's that? Function of x plus h, which is less than, so that area under the curve is bigger than the small rectangle, but smaller than the bigger rectangle. And the area of the large rectangle is function of x plus h times h. So it's that length times h. We okay with that? Yeah, you were just doing this line here that I've highlighted. Sorry, that. Oops, can't get it. There. It doesn't want to highlight it. But that's what I just showed you on a piece of paper, enlarged. Okay, now, the area of DCGE, we came up with that area here, just here. So we've just put that back in there because I just had area DCGE. So they've just substituted that back in there. Now what they've done, what do you think they're doing next? Have a look. Well, I'm going to make this bigger. You tell me what you think they've done next. Yes, you do know. So we did that, and we just did this, but we've just substituted that back in because we worked this out before, the area of DCGE. Tell me what they're doing from this line to the next. What have they done? Come on. No. They're dividing by H. So they've taken this line that they've got, they've divided by H. Now, doesn't this look like differentiating? It almost looks like differentiating from first principles. If you put limit as H approaches 0, this is like differentiating from first principles. Doesn't it look familiar? F of x plus H minus F of x over H. Limit as H approaches 0. So if you've got this inequality here and you just put limit as H approaches 0 in front of each term there, you'll come up with this. Now we recognize this to be the derivative, the first derivative of the function ax. Doesn't this look like differentiation from first principles? So therefore the limit as H approaches 0, well, there is no H here, so it just stays as function of x, will be less than the derivative of ax, which is a dashed x, which is less than, tell me where the mistake is. Oh no, this is okay, because when you put H is 0, which is less than function of x. In other words, the derivative of the function is that function of x there. Okay? No. Anyway, we're just saying that so therefore ax is the primitive of the function of x, and then we just do the substitutions to find the area between a and x by substituting. All right? You just, underneath the notes that you wrote earlier, can you just write this out, please? So therefore the integral between b and a of x to the power of n is x to the power of n plus 1 over n plus 1. Then we put these square brackets because we're going to substitute for b and a. So you already know that the integral, or finding the primitive function of x to the power of n, is x to the power of n plus 1 over n plus 1. But if this is called a definite integral when you've got values to substitute. So when you do that integration, you write the primitive function there, right? You then put square brackets and you write those values of x. The b and a are values of x. You write them there. And then what we do is we substitute the value of b in for the first x value minus, and we substitute the value of a in. All right, now I'm going to do a whole lot of examples on that.